Good morning, class. This is Tim Tomlanovich. Welcome to Structural Analysis. This is your last learning plan. Course Competency 11. Compute wood column sizes from framing system loads. So this is it for your class for structural analysis. All right. So hopefully everybody had a wonderful Easter. Okay. So finally, all right. Learning object. Discuss the importance of consideration of failure modes in columns, differentiate the modes of failure between short and long columns, review loading conditions that may cause failure in short and long columns, and then review column end support conditions that affect failure in long columns, and then review use of bracing with respect to failure of long problems. So let me get my little laser pointer out. Okay, so basically wood columns. So let's define the modes of failure here. Okay, so short columns typically, so the length divided by the diameter, a really small number. If this is just a numerical number, a really short number, short columns will fail by crushing. Okay, however, the larger the L over D number, they call this a slenderness ratio. They will fail by buckling. So just like I was showing you in the example in the class, is when I put a load on there, and then the load, the thing is going to want to buckle in the weak axis. Okay, the weak moment of inertia axis. So that's why we have to determine the moment of inertia around the x-axis and the y-axis. Okay, so long columns will fail by buckling. Short columns will fail by crushing. Okay, so how do we do a short column analysis? It's all related to stress. Okay, so number F equals stress. A is the actual compressive stress. So my load, P, okay, divided by my cross-sectional area of my column, that'll be my actual stress, has to be less than or equal to my allowable stress. And remember, the allowable compressive stress comes from tables in your textbook, codes, okay, when we were in the stress chapter, okay? So, say I wanted to design a column, right? Can I rearrange this equation to solve for A? Say I need to size my column based on my actual load, okay, and my allowable stress, because I want to stay below that. I can rearrange this equation, put A required equals P actual divided by my allowable stress, and then I'll get my required area, and then if it's square, I can just take the square root of that, and then I get my column, and obviously I always want to round up my area, okay? So that's short column analysis. Long column analysis is different. So long columns fail by buckling. Okay. So direction of buckling. Okay. So if you look at this figure here, so this is failing around the y-axis here. See this rotation here, this moment. So it's going to fail in the weak axis. Okay, and that is IY. So I is moment of inertia is less than the moment of inertia in the x direction, okay, because that's the way it's going to buckle, okay? So this is why we need to differentiate between these. This little R term is called a radius gyration. This is another term used in column analysis, so it's kind of hard to explain. So just knowing that I and R are related, as we see down here, okay? So to figure out that critical load before the column buckles, okay, we have to do an equation. So pi, this is pi, 3.14 squared, times the moment of inertia. Oh, I'm sorry, this is modulus elasticity. We find that from tables. By the minimum moment of inertia, that smallest mathematical number. Remember doing that section, smallest mathematical number, okay? The smallest moment of inertia, okay? All right, so from knowing that, and then dividing by L squared, that'll give me my critical load, okay? So if we rearrange P critical divided by area equals my F critical, because P over A, this is a critical stress. So we can convert that critical load divided by my area of my column and turn it into a critical stress. So if we go through all the derivation of the algebra, okay, they found out that the radius of gyration, which is another, I guess, stiffness term, I guess another way to define stiffness, is the square root of moment of inertia divided by the area of that column. So the smaller radius of gyration, okay, is the way it's going to buckle. All right. So with that, so L over R is known as a slenderness ratio. So L over R, or L over D, or L over R, same. Those two terms are used interchangeably. R is a slenderness ratio. So this is how columns buckle. So they're not going to crush, they're going to buckle. So we need to figure out that load before they start bending like this, because we can't buckle. Okay. All right. So let's talk about end support conditions. Okay. So when we turn this column and this basically rotate it 90 degrees, this is a moment diagram. Okay. This is a pin. This is a pin. Okay, so both ends pin, structure adequately braced against lateral wind and earthquake loads. Okay, so this is a typical column or a stud in your house. A pin is actually, you can figure this is nailed into the sole plate, this is nailed into the joist. Okay, there is not enough resistance for it. That will actually be, we assume it's freely allowed to rotate, because remember, a pin reaction, there's only a horizontal reaction here, so it's free to rotate. Okay, so because of that case, the actual length of the effective length is actually the total length. So LE effective equals the length of their column due to the way it's connected to the structure. Okay, so that we have this K term called 1. So basically what we're doing, the full length is going to buckle. So the longer the column, the easier it is to buckle, right? So P critical equals pi squared over modulus elasticity divided by I min over L squared. Okay, now let's take a look at this guy. So there are many more conditions, but these are the typical ones you find in residential construction. Okay, KC, one end pin on one end fixed, structural adequately braced against lateral forces. Okay, so we don't talk about lateral forces. That's a whole nother design. Okay, so this can mimic a column embedded into concrete in your basement. So you know those jack posts that you put in a basement underneath a beam, those are supposed to be embedded into concrete. So if they're embedded into concrete a certain depth, they're not free to rotate. Okay, so before it starts bending, right? So when I try to buckle that column, it's going to start buckling up here, okay? And then it starts buckling. So if you see the moment diagram, it switches from a positive moment to a negative moment here, okay? So moment equals 0. So they call this an inflection point. So here's the actual length of my column, okay? So this isn't gonna, this from here to here is like the rigid zone, and then my actual buckling zone is, they call it L effective. So my K value is actually 0.7. So my effective length is 0.707 times length. So basically my effective length is less. If I look into this equation, if I divide this equation by a smaller number, I get a larger critical stress. Okay, so that's how that works. All right, let's talk about bracing. Okay, so as we know, when we load up a stud wall, right, which way is it going to buckle? It's actually going to buckle inside the wall. It's not going to buckle out, because going strong axis is this way. Okay, so LX, the length of my stud between top plate and bottom plate, is LE. Okay, all right, so say I need to prevent buckling. So what we can do, that's why we put bracing in. Okay, so what that will do will actually reduce the length, our effective length. Okay, so it will help the weak axis. Okay, this is the same reason why we put cross bracing in floor joists. So your floor joists are loaded, how the joists are oriented, we got to put those blocking in. So when that load comes out, the joist will actually want to deflect sideways. So that's why we put that. That's the weak axis. That's why we need to put lateral bracing in there. Okay. So if you look here, here's no bracing. Here's bracing at mid-height. See, our effective length is L over 2, so that means we can put more load on there, and so on here. Third point bracing, asymmetric bracing. Okay, so this is why you see bracing in certain parts, especially in steel. Because if we look here, here's my y-axis, so this thing is going to want to buckle toward into this bracing. So that's why we have bracing, so it doesn't buckle due to the loads. Okay. All right, let's do an example. Okay. Here we go. So example 1, determine the Euler buckling capacity. So that's P critical of the timber pole, a length of 24 feet used in carrying a major roof load. The pole has a 10-inch diameter and is considered pin connected at the top and bottom. Assume the modulus elasticity equals 1.0 times 10 to the 6 psi. Okay, so what I'm going to do is I'm going to switch to my document cam, and let's do this example. Okay, I'll go back example 1. Okay, so what is it wanting us to ask? Determine the Euler buckling capacity. So we're going to do it in both in terms of load P and stress. Okay, so does this look familiar? So find. So this is example 1. Okay, P critical, which equals, so I'll go back to my pi squared times the modulus elasticity times my moment of inertia divided by the length squared. Okay. All right, so here's P critical. Let me zoom in a little bit here. There we go. Here's example 1. Let me auto lock here. Okay, so we know what pi is. Equals pi. So modulus elasticity. Okay, so we got to look at the givens here. Oops, we'll do 2 examples here. Modulus elasticity 1.0 times 10 to the 6 pounds per square inch. So where do I find this? Where do I find modulus elasticity? That's in design tables. Okay. Moment of inertia. Uh-oh. All right, moment of inertia. Okay, so remember these tables? Circles and stuff? So if I look here, here's moment of inertia. It is a solid, let me zoom in here. It's a solid circle, assuming it's a solid pole. The moment of inertia around the x-axis and the y-axis is the same because it's symmetrical. So that equals, if I zoom in here, that equals pi d to the 4th, diameter to the 4th, over 64. Okay, so I'm going to write that formula down. Pi times the diameter to the 4th over 64. So that is my moment of inertia. Okay, so there it is right there, pi d to the 4th over 64. Okay, so we want to find our weakest axis because that's where it's going to buckle. So a circle, that's why circular columns are commonly used, because there is no weak axis. Well, I shouldn't say that. They're the same no matter which way the direction goes. Okay, so we have my I min. Okay, and then my length equals, if I go back to the problem, is 24 feet. Okay, however, we're in inches. We're going to turn this into inches. Okay, so, and I got to calculate this. I'll do that in a second. So, times 12 inches per foot. That equals, so 24 times 12 is 288 inches. okay? Because we need the units to cancel out. All right, so this equals pi times diameter. Our diameter is 10 inches, so we want to keep this in inches, so we have this in inches, because moment of inertia is inches to the fourth times 10 inches. I just raised the 10 to the fourth divided by 64, and that equals, so second pi, where's my pi on this calculator here? There it is. Pi times 10 raised to the fourth divided by 64. I get 490.87. So I'm going to say 400, just to round down to whole numbers, 400, always round, I'm going to go 490 inches to the fourth. Okay? All right. So now, do I have all my variables? I have pi, I have modulus elasticity, a moment inertia, and length. So now I can find my P-critical. So step 1, step 2, I'm defining all my variables. Okay, so 2. So 3, I'm going to solve. All right, so pi squared times 1.0 times 10 to the 6. 6 goes, it's an exponent, not a subscript, times 10 to the 6 pounds per inches squared times 10 inches raised to the, oops, not 10 inches. I'm thinking about the other formula. I times 490 inches to the fourth, okay, pi squared times modulus elasticity times 490 inches to the fourth divided by my length squared, inches squared. So if I look here, I am looking for a P, which is a load, right? Load in pounds. So these inches, so pi squared times E times I, okay? So this ends up, everything cancels out, and we end up with, so I'm going to make sure I have the right equation here. I'm not missing something here. Okay, pi squared times E mine. All right, buckling in pounds. Yep, that's right. So all the units cancel out. Pounds per square inch, inches. This is where I'm getting confused right there. I'm going to make sure. Here we go. I want to square this term. All right. Okay. So this is so I have inches squared here, left here, and then inches squared divided by inches squared. Those cancel out. Now I'm left with pounds. There we go. All right. So let's plug that in our calculator. Okay. So pi, shift pi. I'm going to square that term times 1.0 times 10 to the 6th times 490 divided by 288 squared equals 58,305. 305 pounds. Okay, I'm just going to double check my math here. Shift pi squared times 1.0 times 10 to the 6 times 490, okay, divided by my length squared. Yep, 58,000. So this equals my P critical. Okay? All right. So let me zoom out so you can see my calculations here a little bit. So that's my critical load before this column buckles. Okay? So now let's find our actual stress. That's F, right? Equals P critical divided by my area. Okay, so area equals pi times d squared over 4 equals pi times 10 inches squared divided by 4, because our diameter of our column is 10 inches. So pi times 10 squared divided by 4 is 78.54 inches squared. Okay, so now my allowable stress, or my actual stress from the critical load, is 58,305 pounds divided by 78.54 square inches, and that equals 58,305 divided by 78.54 equals 742. So I'm going to round it up, 743 pounds per square inch, and that has to be less than or equal to my allowable stress. Okay, that has to be equal to or less than allowable stress. So so what we do in column design, we kind of do both at the same time. We see if we're not going to crush it, right? So we always have to check crushing, even though it's going to buckle first. Okay, so once we find that critical load for buckling, we always got to check that we're still below our allowable stress based on the tables. Okay, so that means, so if we're basically, what happens is, if our actual stress from our critical load exceeds our allowable stress, that means it's going to crush. So we're going to have to reduce our load back down to the allowable stress, and then that P critical will be less, or this load will be less than our P critical. So now we won't crush or buckle. Okay, so this typically does not happen. Typically, the buckling critical load is the one that governs in a column design. Okay, so that is that example. So we found the critical load. Okay, so now that we found the critical load, if we go back to this example, right? So now you can check as you do load tracing. Okay, load tracing, as you'll find, this is my load. So I'm going to go to the slideshow now, because we'll go on to another. Well, I'll just keep it there. So my load here, right, is that less than or greater? My load from load trace, is that less than or greater than my critical load? So if it is, we're going to have to do something different here. We're going to have to make this column bigger, right? Or we're going to have to reduce the load somehow, or we're going to have to reduce the span. So there's a lot to think about when we're doing design of columns. Okay, so let's do another example. So this isn't steel column, so this is actually wood column. So you want to change that in the slide. I'll put the new ones in Blackboard there. Wood column and example 2. All right. Determine the Euler buckle capacity of a timber pole. What did I do? I copied the wrong way. We just did that one. So I'm going to pause for a second and get you the right one. All right. So sorry about that. I got to copy the wrong problem here. So, all right. Example 2. So determine the buckling load of a 2x6 S4S surface on 4 sides stud wall 14 feet high and braced at mid-height. Okay. Assume a modulus elasticity of 1.4 times 10 to the 6 psi. My allowable compressive stress of 100 psi. Top and bottom connections are pins. So again, like I was saying previously, because we're just nailed to here and here, that's a pin action, so it can rotate. Those nails are not going to resist any overturning or any moments. Okay, so that means our K effective, our L our effective length L is the full length of the column, okay? Just like in the last example, okay? The L squared on the bottom, see, we assumed they were pins, so I did not do any effective length change in that, okay? But so when we brace it though, we will, okay? So here, let's go through example 2. All right, so example 2. All right, so let's write down our givens. Okay, I'm going to write them down as I'm talking to you, and I'll show you the engineering paper. All right, determining a load of a single 2x6. So 2x6 S4S. Okay, S43 I wrote instead of S4S. Okay, my L equals 14 feet. Okay, and then also it wants to do us at a L at 7 feet. At 7 feet too. L at 7 feet, then L equals 7 feet. Okay, so basically we're reducing length because that bracing is acting like a pinned connection at 7 feet then. Okay, my modulus elasticity equals 1.4 times 10 to the 6 pounds per square inch, and my allowable compressive stress, because it says a capital F, it's capital, equals 1,000 pounds per square inch. Okay, top and bottom are pin connected. All right, so first thing we got to do is, all right, okay, so let me go back to the document cam. All right, so here's example 2. So we know it's a 2x6 S4S, okay? My length is 14 feet, and then my length is 7 feet. So I'm going to put LE here, okay? It's 14 feet without bracing. It's 7 feet with bracing, okay? This stays the same, and this stays the same, all right? So looking into tables, if I look here, it's a 2x6, right? 2x6. Surface dried actual dimensions. Okay. I can actually get my area right off the chart here. So a 2x6, because I'm going to know I'm going to need my area. Okay. That equals 8.25 inches. So I look right here. Area, inches squared, of a 2x6 is 8.25 inches. So, okay. All right, now I need to know my moment of inertia. Okay. I equals BH cubed over 12. So, okay, if I look here, but this, remember, they're assuming, okay, let me get this out of here. I'm probably going a little too fast. So this is assuming the strong axis. This is assuming the strong axis, okay? So with that, so we need to actually find our weak axis, right? Our strong axis. So let me zoom in here. Okay, our weak axis, right, is the y direction. Okay, is the y direction. So IY is HB cubed over 12. Okay, HB cubed over 12. Okay, so with that, IX equals BH cubed over 12. My moment of inertia in the y-axis equals HB cubed over 12. All right, so let's do my, so I'm looking down at it. So my B is 1.5, my H is 5.5. So this equals H This equals B. How do I know that? I can look at my chart. 2 by 6 is a 1.5 by 5 by 5. Okay. All right. So, because I need to determine the weak axis, because that's the way it's going to buckle. All right. So B is 1.5 times 5.5 squared divided by 12, and H is, so we just reverse this equation, times 1.5 squared over 12. Okay, so let me move this over. So I plug and chug these into the calculator. 1.5 times 5.5 squared divided by 12. So I get 3.78. So this equals 3.8 inches to the fourth. Okay. And if I look 2 by h cubed. I didn't. That's why I saw it. This looked a little key. This is cubed, not squared. My bad. Say that looks a little small. Okay. 1.5 times 5.5 cubed divided by 12. There we go. 20.8 inches to the fourth. 5.5 times 1.5 cubed divided by 12 equals 1.5 inches to the fourth. I'm just going to do that. 5.5 times 1.5 cubed divided by 12. Yep, 1.5 inches to the fourth. So now looking at the problem, we know the weak axis is, this is, so my x-axis is this way, so it's not going to buckle out into the page. Okay, but it's going to buckle in towards the bracing inside. That's how studs will buckle. Okay, because the y-axis is this way, and if I rotate around this way, it's going to buckle parallel to the wall. Okay, not perpendicular to the wall. Okay, all right, so knowing that, okay, so let me go back to here. Okay, so that's my givens. Okay, so P critical. All right, so let's say L 14 feet equals pi squared times E times I min times my effective length squared. Where did that formula come from? Right there, P critical. Okay. So you notice I'm just going to bring this. You notice I'm not really worried about the radius of gyration. That's another way to find the same answer, but we're just going to stick with this guy right here. This is the effective length. Okay. All right. So my P critical at 14 feet. So pi squared times 1.4 times 10 to the sixth times my minimum modulus, or my minimum moment of inertia, which is in the y direction, which is 1.5 inches to the fourth. I don't need units because they all work out. Divided by my effective length. So we're doing the unbraced length, so I'm going to use 14. Okay, that's my effective length. So do I put 14 in? I know I have to put it in inches times 12 inches per foot. So this equals, I know this is 84 inches. 14 times 12, 168 inches. Okay, 7 times 12 is 84 inches. Okay, so this is 168 squared. Sure your units are like. Okay, so pi times 1.4 raised to the 6 times 10 to the 6 times 1.5, okay, divided by 168 squared. So this equals 233 pounds equals P critical, okay, at 14 feet, okay? So let's calculate our actual stress equals P critical divided by our area, which equals 233. Actually, we'll make it round up, make it a worst case scenario. It's 233.7, so I'm going to make this 234. 234 pounds divided by, I know my area, that's why I wrote it down because I'm going to need it, equals 8.25. Okay, so 234 divided by 8.25 equals 20, I'm going to say 29 psi, which is less than 1,000 psi. We're good. Okay, we're good. So my critical load is 234 pounds per stud. Okay, I'm not crushing it. And as long as when I do load tracing, when I go back to the problem, is that what is my load per stud when I load trace? That I'm underneath that critical load. That'll determine if I need lateral bracing or not. Okay, so that was on the 14-foot length. Okay, so now let's do the effective length of 7 feet. So P critical L 7 feet equals pi squared times 1.4 times 10 to the 6. That's modulus elasticity. My weak axis is the same, 1.4, 1.5. Okay, divided by, so now my effective length is 7 feet because remember, I'm putting bracing in now. Say my load is exceeding my critical load for a 14-foot length. So what I can do is put bracing in. That will allow me to increase my load. Okay, so if I do that, so that is 84 squared. 84 inches squared. The number is squared. Okay, all right. So shift pi squared times 1.4 e to the 6th times 1.5 equals divided by 84 squared. So now my P critical, look at this, equals 2,937 pounds. So as you can see, from a 14-foot length to a 7-foot length, see how much more I can increase my load for buckling? That's pretty amazing, isn't it? But now, okay, we got to check our actual stress equals P critical. Okay, let me use so you can see what I'm writing. Divided by area again. So now we got 2,937 pounds divided by 8.25 square inches. Okay, equals 2,937 divided by 8.25. That equals 356 psi, and we're still less than our allowable, right? Which is 1,000 psi. So we're good. Because remember, our allowable stress from code tables was 1,000 psi. So as long as we're less than or equal to, we're good. Okay. All right. So now we can hold up to almost 3,000 pounds, depending on the load trade. So that allows us to increase our loads on the studs. So, okay. So that was example 2, wood column analysis. Okay. So moving on. All right. So let's just talk about the general process of wood column design. So going through these examples, I kind of did it already. All right. So first we want to find the required cross section area for crushing. Okay. So from load tracing, you put your actual load in there. Okay. Here's my actual divided by my actual area equals my actual stress is less than or equal my allowable stress. Okay. However, like I showed you before, A required equals my actual load from load tracing divided by my allowable stress. That'll give me my area. Okay, so when you do this is kind of like a trial and error basis. We're just starting with crushing. Okay, so we're going to find that area required for crushing. Okay, based on my load from load tracing, and then we're going to kind of check it for buckling. Okay, all right. So 2, calculate the largest effective buckling length. Okay, what's my case? Am I putting bracing in here? Okay, this is my effective length, L times K. All right, so basically you're in this case here or this case here. Worst case scenario, you're here, right? Nailed, nailed. Basement beam post embedded in concrete, nailed to the floor beam. Okay, all right, so you find your largest effective buckling length. So base, okay. So if you need to, then you start considering bracing. Okay. Step 3, calculate the slenderness ratio. Okay. So the slenderness ratio is effective length divided by my minimum diameter. So so the previous example was 1.5 inches or 5.5 inches, right? So around less than or equal to 50, we should be okay for a slenderness ratio to help prevent buckling. Okay, so if we take, okay, so it was 14 feet times 12, right? In the previous, it was 168 inches divided by 1.5. Oh boy, you ready? So I get 112. So we're not doing good. Okay, we're not doing. So typically that's kind of a long stud without bracing. Okay, so now I'm going in a little more advanced analysis here. Okay, all right. Then we're going to calculate the Euler buckling stress. Okay, so now so the previous 2 examples were just getting an idea of critical stress, critical load. How do you calculate that? Why is it working? Why do columns buckle? Okay, so now what we're doing is we're actually we're putting factors of safety in here due to wood defects, loading conditions, etc. We're kind of going one step further. Okay, critical Euler buckling stress. Okay, KCE is 0.30 for visually graded lumber, Menards lumber, or 0.418 for glue rams. Okay, these numbers. Well, this is from your textbook. Okay, this is from chips and defects and stuff because wood is not perfect. Okay, that times my modulus elasticity divided by my slenderness ratio squared. Okay, this is another way to calculate that stress instead of doing P critical, is my Euler buckling stress. Okay, so F, Euler is stress, CE. Okay, Euler buckling stress. Okay, from my slenderness ratio. Okay, all right. Okay, let's see, that was step 4. Step 5 is calculate the adjustable allowable stress parallel to grain due to load duration. All right, let's talk about this. All right, so looks like it's hard to see. Format. Just gonna squeeze that down a little bit just so we can actually see it. Okay, slideshow. All right, so load duration. Okay, basically let's talk about this. So is it permanent? Is it a permanent load? Okay, the load duration is 0.9. Okay, 10 years normal load 1.0. 2 months snow load 1.15, 7-day 1.25. So basically what is saying is that I can increase my load on that if it's a short-term load. Okay, if it's a short-term load. Okay, so typically what we do between 0.9 and 1. So when we're actually saying it's a permanent load, we're actually reducing the stress on that by 10%. Okay, so if it's an impact load, basically it's a 3-second load. So it comes on there, so we can actually increase the stress on there because it's so short term by a factor of 2 and 10. Okay, so most of our loads are permanent, right? So snow load, when this is key on roof loads, would you agree? So would you feel comfortable increasing a snow load of 1.15? According to the code, we're okay, right? But if you're up in Alaska, if those snow load stays up there forever, I don't know. That's a good question, isn't it? Okay, so anyway, so typically 1.0 or 0.9, okay, load factor. So this is allowable compressive stress based on design manuals times my load duration equals my allowable stress. Okay, so then from that, calculate U critical stress divided by a adjusted stress ratio. Okay, so this is my critical Euler stress divided by my adjusted allowable stress based on load duration. That's a factor. Okay, and then determine the column stability factor, CP, from the ratio calculated from step 6. This can be found on page 9.3 of your textbook, and I can show you an example of that. As soon as I find it here. Here we go. I'm going to switch. Okay. Okay, so here is that ratio I'm talking about. So there's a stability factor here. Okay. All right. Calculate the allowable design compressive strength. F prime C equals, okay, is F prime C star is the adjustable allowable compressive stress based on load duration. So that's from the design table times CP equals allowable design compressive stress. Okay. So that's where that CP comes. All right. Now calculate my allowable load, F prime C, okay, divided by my A equals my allowable load. All right. Oops, sorry. And then step 10, my P actual better be less than my P allow. Okay. All right. Lots of information there. How about we go through an example? Okay. So when you read the book, it's kind of cluttered in there, so I kind of created a step-by-step process for you. Okay. So let's do an example, and then this hopefully will make more sense. So I can sit here and read these slides, but until you actually get into it, it won't make sense. All right. All right, so here we go. So we'll design a column. Design a solid sawn square column 14 feet tall to support an actual load of 10,000 pounds. Assume Hemfer #1 material with the top and bottom pinned. Okay, so let's write down what we know. So solid, that means we're not using dimensional lumber. Okay, it's a rough sawn. It's not S4S. Okay, so length equals 14 feet. Okay, this is example 3. Okay. All right. Actual load of 10,000 pounds. P equals 10,000 pounds. Okay. So the previous two examples were actually analyzing existing columns, given stuff. Now we're actually designing a column when I don't know the size of it. Okay. All right. So hem fur. So we're using hem fur number 1. Okay. Hem fur number 1. All right. Is there anything else? So if I look at here, all right. So let's go back to step 1. All right. Step 1. Okay. So I'm going to go to, all right. Here's what we know. So let me bring this up so we can see what I'm doing here. And let's do an autofocus. All right, doesn't want to focus. There we go. Focus lock. All right. Step 1, find required cross-sectional area. So A required equals P actual. That's from my load tracing divided by my allowable stress. Okay, so I know what's define our variables, or P actual equals 10,000 pounds. Our allowable stress, where do I find that from? Remember this table, 5.2 from your textbook? All right, so I'd say we're using hem fur number 1, right? Beams and post. Hem fur number 1. Okay, so that means my allowable compressive stress. So when it's a column, allowable actual compressive stress, we're using FC. Okay, that's parallel to the grain, because a column we're using parallel to the grain. Okay, and beams and posts, so it's 850 psi. Okay, remember, don't use this one. That's perpendicular to the grain. We're parallel to the grain. So hem fur number 1 is 850 psi. So F allowable, FC interchangeable terms. Allowable, 850 pounds per square inch. Okay, so my required area, so I don't crush it, equals 10,000 pounds divided by 850 pounds per square inch, and I divide that out. .76 equals 11.76 square inches. So I want to round up, because remember, force over area equals A actual, right? P over A equals actual stress. Okay, so if I round this up, if I make my area bigger, my stress will be. So let's just round this up to 12 square inches. All right, so now I need 12 square inches, okay, of area. Okay, so before I'm going to continue with the design. Okay, before I figure out my column here, okay, because I don't want to select something and then it doesn't meet Euler. It doesn't meet what am I trying to say? The Euler critical stress. here, okay? So this for right now, I can say a 2x10 will work. But do you really think, because there's a weak axis, right? So I would want to go square, because I know my y-axis and my x-axis is the same. So already I can use a 6x6, okay? All right, so I'm just looking at my area, but the problem is saying rough sawn, right? It's saying rough sawn, okay? So right now, A equals the square root of 12 square inches, or x equals the square root, okay? So you can either go to the table, sorry I keep kind of jumping around here, so it's going to be a 5.5 or a 5.5, but the problem is asking what? The problem is asking for rough sawn wood. So I'm going to cut this out at a sawmill, okay? So if I just take the square root of 12 inches, it's 12 square inches. All right, so square root of 12. So 3.46, 46 inches. So I'm going to say, for now, let's do a 4-inch by 4-inch rough sawn column. Okay, so now my area is 16 square inches, right? Okay, all right. So now if I take 10,000 pounds divided by 16 square inches, my stress is only 625 pounds per square inch, and my allowable is 850 pounds per square inch. Okay, so I'm going to say F actual equals P divided by area. So that's 10,000 pounds divided by 16 square inches, and that equals 625 psi, which is less than 850 psi. So we're good. Okay, I want to make sure my actual is less than my allowable. Okay. All right, so that was step one. Sorry, I kind of jumped around on all that. I apologize for that. Okay, so find my area required based on my allowable stress from the design table. Okay, once I find that, round it up. Okay, because it's going to be rough sawn. Okay, take the square root of it because we want to be squared. That way I don't have a weak axis, right? I have my IX and my IY are the same because it's square. Okay, round it up and check my actual. I'm less than my allowable. We're good. Okay, so that was step one. All right. Step two, calculate the largest effective buckling length. Okay, so I know that my LE equals L because I'm going to assume 2 pinned ends, it's just going to be nailed. Okay, so that equals 1.0. Okay, all right, so that's step two. So LE equals L. So, well, I'll do it equals L times K. So, which equals 14 feet times 1.0 equals 14 feet. So might as well get this in inches, divided 12 inches per foot. So 14 times 12 equals 168 inches. Okay, so this is my effective length. Okay, because the problem said it's pinned, and this is typically the worst case scenario. Okay, all right. So that was step two. Step three, calculate the slenderness ratio. LE over D min. Okay, and that needs to be less than or equal to 50. Okay, so my effective length is 168 inches. Okay, divided by my D minimum is 4 inches. Okay, 168 divided by 4, so it is 42. So that means it's less than or equal to 50. We're good. Okay, effective length divided by my minimum dimension. We're going to use square. We use the 4 by 4, so we're less than 50, so we're good. So we have a good chance that we're not going to buckle. Okay, if it's over 50, then we want to make. What do we want to do? How do we make this bigger? Okay, so that's step 3. Step 4, calculate Euler buckling stress. So I'm going to write the formula down. FCE equals KCE times modulus elasticity divided by my slenderness ratio squared. Okay, so FCE, I'm using rough sawn lumber, or I'm sorry, KCE. Write down my variables here. All right, visually graded lumber, 0.30 modulus elasticity. Okay, modulus elasticity, Hemfer number 1. Where do I find that information again? Okay, let me zoom out, push the paper up. Modulus elasticity, Hemfer number 1. Modulus elasticity, it's right here. Hemfer number 1, beams in post, 1300 KSI, or 1.3 times 10 to the 6 PSI. Okay, that's a point. Okay, and then my LE over D equals 42. All right. Okay, so my Euler critical buckling stress, FCE equals KCE, which equals 0.30 times 1.3 times 10 to the 6th divided by 42 squared. Okay, so if you look here, so we got to do this and divide it by this. So you got to make sure you square this term before you divide. Don't square it after you divide by, okay, for order of operation. So from that, we get, all right, 0.3 times 1.3 times 10 to the 6th divided by 42 squared equals 221. Okay. 222 pounds per square inch. I'm just going to redo this here. So 0.30 times 1.3 raised times 10 to the 6th equals divided by 42 squared equals 222 pounds per square inch. Okay? Euler critical buckling stress. All right. So what happened here? Let's look here. Is this is my buckling stress. Instead of load, what is my actual stress? 625. Okay. What does that mean? Do I need to make my column bigger? because it's going to buckle? Yes. Okay. So now basically what we do, so it's before we even move forward, all right, before we move forward to figure out the calculated load, we're going to have to get our stress. I just wanted to just double check here. Adjustable allowable stress parallel to the grain. Okay. Well, let's just keep going through this, and then we'll make adjustments at the end, okay? Because I can't remember if this is adjusted for later, okay? So in the meantime, so we have this number. So if I go back to this number, and if we go to, this is our actual stress right here, okay? So these two, I have a feeling that because this is greater than this, we're going to have to make this bigger, okay? So, all right, so this is page 1 of 2, okay? So now, example 3, page 2 of 2. I should be able to get this on 2 pages. All right, let's go back. All right, so we calculated our Euler critical buckling stress. All right, step 5. Calculate adjustable allowable stress parallel to the grain due to load duration. Okay? I want to make all my adjustments at the end here. So, F prime C equals FC, or F allowable, times CD. All right? So, permanent load, if it's a column, we're going to say CD equals 0.9, worst case scenario. Okay. All right. And then our allowable compressive stress, basically hem for 1, was, if you look at, we already defined this from right here, 850 pounds per square inch. That's hem for 1, and that came from this table right here. Allowable compressive stress is 850, okay, because it's a permanent load. So FC equals 850 pounds per square inch, okay? So F star C equals 850 times 0.9, and that equals 850 times 0.9 equals 760 pounds per square inch. That equals F star C. Adjustable allowable stress due to load duration. Creep. Basically, wood will creep and it'll deteriorate. It gets moist. Okay? It could have a crack in it. Okay? So that's step, this was step 5. Okay? All right. Let's go to step 6. Calculate Euler critical stress adjusted stress ratio. Okay? So step 6, we go to FCE divided by F prime C, okay? So that equals, so from step 4, here's our Euler critical stress, 222 pounds per square inch, divided by, all right, so 765 pounds per square inch. So it's a ratio, so that's a unitless number. Okay. Equals 222 divided by 765. So I get 0.290. Okay, that was step 6. Okay, all right. Step 7, determine stability factor CP from the table in the book. All right, so let me find my piece of paper here. I have it here somewhere. Here we go. Okay, so if I go to here, I'm going to zoom in here. All right, here's the CP value. Okay, so if you look, there's 2 different columns. We have SON and glue lamp. So we're in the SON column. Okay, so now we got to find 0. What do we have? 0.290. So if we have to, we can interpolate between. Okay, or you just figure out over time, you know which one is the worst case scenario. So if I look here, here's my FCE. So this is my Euler critical stress divided by my adjustable allowable stress due to load duration. Here's that ratio. So I come down here, I find 0.290, and then I'm in the sawn lumber category, and I have 0.270. 0.270. Okay, so right there, sawn 2.9, 0.270. Okay, so that's my CP value. Okay, all right. All right, calculate allowable design compressive stress. Step 8. F prime C equals my adjusted allowable compressive stress based on load duration times my CP factor, my column stability factor. Okay, so we get 765 psi times 0.270. Okay, that takes it. Basically, what that does is the book goes in a great amount of detail. It takes apart for defects in wood, knots. It's visually graded by people, so it provides factors of safety. That's what it does. Okay. Oops. So 765 times 0.270. So basically 206.55. So I'm going to say 206 psi equals F prime C allowed. That's our adjustable factor. First we started with what? First we adjusted it by load duration. Okay. So sometimes we increase it, sometimes we decrease it. Typically you're decreasing because there's a permanent load. Okay, and then we're finding that CP value, and then we're reducing it again. So this is basic. Okay. So even to go back further, we started with here's the stress that it's going to buckle at. Okay, that's the stress it's going to buckle at. Okay, then we went to the load duration. We reduced the allowable stress. Okay, and then the allowable stress based on defects and factors of safety. So this is the final allowable stress that we can put on that column. Okay, so all right. So that was step 8. So now, okay, so step 9. So this is a good thing I hold this because I knew we would figure this out later. Step 9, now calculate the allowable load. P allow equals my final adjusted allowable compressive stress based on all the load factors times area. Okay, but don't we have to design? Don't we know our load has to be 10,000 pounds, right? This is a given value, so don't we want to back calculate an area now? Okay, so initially, what did I assume? I assumed that keep it from crushing, we're going to use a 4x4, right? Okay. However, it's going to buckle before it crushes. It makes sense because it's a really long, it's a long column. It's 14 feet. So this typically buckling will take precedence over crushing. The column will buckle before it crushes typically. Okay. So that's why I did not keep readjusting the size of this column here, because I knew I needed to find my final allowable stress based on the critical Euler stress, etc. Okay. So now knowing that, can I rearrange this equation to find my area? Absolutely. So P. So yep, P allow, or P whatever it is, divided by F prime C equals area. Okay, so I know I have 10,000 pounds divided by 206 pounds per square inch. Okay, so 10,000 pounds divided by 206, and I get 48.54 square inches equals area. Okay, so x squared equals area. Okay, all right, so that equals x equals the square root of area. Okay, so we take the square root of that answer, 48.54, and I get 6.96 inches. Okay, so I'm going to rough cut a 7-inch by 7-inch rough sawn column. Okay. Okay. So as you can see, that is a lot bigger than this guy. So if I take 10,000 pounds divided by 49, my stress is going to be a lot less than 850. Okay. So my actual stress equals 10,000 divided by 49. Okay. Divided by 49, which equals 204 psi, which is less than this guy right up there, my critical stress. Which is even less than, see, we're not even worried about crushing anymore, are we? We're worried about buckling, okay? Because stress, load, and area, PA and stress are all related to each other, okay? So we're okay, all right? So step that the actual column load is less than or equal to the allowable load, okay? So basically I did this, all right? Okay, so we can do step 10. Let's just check that. So P actual equals 10,000 pounds. Okay. P allow. So now, so if I just go back up to this equation, P allow is what? So 206 psi times, so I did it backwards, okay, times my area of my column is 49 square inches. So 206 times 49 is 10,094. So my P actual is less than or equal to my P allow. Okay, so basically what did I just do there? As you look here, I started here. Instead of finding my P allow, I wanted to find my area because I knew I had to increase my area. I went through the calculations and then I just did a final check that this is actually true. So that's how we do a column design. So from start to finish. Okay. So with that, I do believe we are done. Oh, oh, there's my actual column design. Here's your homework. Okay. Actually, I didn't need to change that. I just did that example. What did I just do? All right, that's fine. Anyway, all right. So I just did that problem. Okay. And here's your homework. Obviously, there's no CC11 homework. Okay. So here's your homework. And then I will submit a quiz. So that's all we have for today. Thank you so much.